Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today we'll examine several illustrated examples of parallel DC circuit analysis. This lecture operates under the presumption the viewers survive the Parallel DC Circuit Examples Level 1 lecture with their sense of dignity still intact. If you haven't watched this lecture yet, by all means take the time to do so now and return to this lecture when you are so qualified. You note the problems in the aforementioned Parallel DC Circuit Examples Level 1 lecture were total setups, so easy that even a snowboarder could do them. Not so in this lecture. These represent more complicated boss-level challenges that necessitate complete mastery of parallel DC circuit properties and a little creativity and thought on your part to achieve the desired results. Take your time and struggle with these problems, and don't tap out too quick. If you can solve these problems, you're tracking. If you can't solve these problems, you do not understand parallel DC circuit properties as well as you think you do. Let's see how it goes. My sincere advice for every single one of these scenarios is to lay out everything you do know about parallel circuits and apply these fundamental properties to the circuit in question. Ideally, you should be able to use the provided clues to make deductions about or to solve for other properties. You will no doubt recall that voltage across elements in parallel is the same. This is the most fundamental parallel circuit property. Additionally, Kirchhoff's current law states that for any node, the summation of incoming currents equals the summation of outgoing currents. In short, what goes in must come out. Finally, power in always equals power out. We can use this fact to solve for other properties or to check our work. Mastery of parallel DC circuit analysis necessitates active participation on your part, and as such, I'm encouraging you to please pause this lecture when asked to do so and attempt example problems on your own. If your answers do not match those illustrated, by all means feel free to rewind the lecture and correct any mistakes you may have made. Our first illustrated example features an unknown voltage source providing 100 mA of source current to a parallel combination of R1, a 270 ohm resistor, and R2, a resistor of unknown magnitude. The only other additional piece of information we're given is that I2 is 40 mA. We're being asked to solve for the voltage drop across each element, the current through each element, the power dissipated by each element, the source current, and the total power. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Voltage across elements in parallel is the same. For this circuit, E equals V1, which equals V2. A Kirchhoff's current law analysis of this circuit demonstrates that source current splits into two paths, I1 and I2. The Kirchhoff's current law equation for this circuit is I source equals I1 plus I2. An algebraic rearrangement of the Kirchhoff's current law for this circuit, solving for I1, demonstrates that I1 is the remaining 60 mA of current. An application of Ohm's law demonstrates that V1 is 16.2 volts. Voltage across elements in parallel is the same. For the circuit, E equals V1, which equals V2, and they all equal 16.2 volts. Total power supplied to the system is equal to supply voltage times source current. Substituting our given values yields 1.62 watts. The power dissipated by resistor 1 is equal to the voltage across it squared divided by resistance. Substituting our given values yields 972 milliwatts. If total power equals P1 plus P2, an algebraic rearrangement of this power distribution formula, solving for unknown power P2, demonstrates that P2 is equal to P total minus P1. Substituting our given values yields 648 milliwatts. An application of Ohm's law solving for R2 demonstrates that R2 is the voltage across it divided by the current through it. Substituting our given values demonstrates that R2 is 405 ohms. As a means of checking our work, the total resistance of R1 and R2 in parallel is 162 ohms. Solving for source current, where source current is equal to supply voltage divided by total resistance, does indeed yield 100 milliamperes. I've got a reasonable degree of confidence these answers are correct, and we can move on to the next illustrated example. Our next illustrated example features an unknown voltage source providing power to a parallel combination of R1, an unknown resistor, and R2, a 400 ohm resistor. It is additionally known that the total resistance seen by the source is 300 ohms, and the power dissipated by the second component is 1 watt. We're being asked to solve for the voltage drop across each element, the current through each element, the power dissipated by each element, the source current, and the total power. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Voltage across elements in parallel is the same. For this circuit, E equals V1, which equals V2. Kirchhoff's current law. Source current splits into two paths. For this circuit, I source equals I1 plus I2. Finally, power in equals power out. For this circuit, power total equals P1 plus P2. You will no doubt recall that power dissipated by the second element is equal to V2 squared divided by R2. An algebraic rearrangement of this formula solving for V2 demonstrates that V2 is 20 volts. Voltage across elements in parallel is the same. For this circuit, E equals V1, which equals V2, and they all equal 20 volts. Source current is equal to supply voltage divided by total resistance. Substituting our given values yields 66.7 milliamperes. I2 equals V2 over R2. Substituting our given values yields 50 milliamperes. An algebraic rearrangement of the Kirchhoff's current law equation for this particular circuit solving for I1 demonstrates that I1 is equal to source current minus I2. Substituting our given values yields the remaining 16.7 milliamperes of current. R1 equals V1 over I1. Substituting our given values yields 1.2 kiloohms. P1 equals I1 squared times R1. Substituting our given values yields 333.3 milliwatts. Power total equals P1 plus P2. Substituting our given values yields roughly 1.3 watts. As a means of checking our work, power total is also equal to supply voltage times source current. Substituting our given values similarly yields 1.3 watts. I've got a reasonable degree of confidence our answers are correct, and we move on to the next illustrated example. Our next illustrated example features a voltage source of unknown magnitude and a parallel combination of R1, an 800 ohm resistor, R2, a 120 ohm resistor, and R3, a 480 ohm resistor. An ammeter installed in this circuit indicates 625 milliamperes of current in the indicated direction. We're being asked to solve for the voltage drop across each element, the current through each element, the power dissipated by each element, the source current, and the total power. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Voltage across elements in parallel is the same. For this circuit, E equals V1, which equals V2, which equals V3. Kirchhoff's current law. For this circuit, source current comes out and splits into three paths. The Kirchhoff's current law equation for this circuit is I source equals I1 plus I2 plus I3. You will note the ammeter is capturing both I2 and I3. Finally, power in equals power out. For this circuit, power total equals P1 plus P2 plus P3. Given the ammeter is capturing current through R2 and R3, this is a perfect setup for the current divider rule. Current is known in a parallel combination of two known resistors. An application of the current divider rule, solving for I2, demonstrates that I2 is 500 milliamperes. Given 500 milliamperes of the incoming 625 milliamperes is routed through R2, an application of Kirchhoff's current law for just these two resistors, solving for unknown current I3 demonstrates I3 to be the remaining 125 milliamperes. An application of Ohm's law demonstrates that V2 is 60 volts. Voltage across elements in parallel is the same. E equals V1, which equals V2, which equals V3, and they all equal 60 volts. An application of Ohm's law solving for I1 demonstrates that I1 is 75 milliamperes. Source current is equal to I1 plus I2 plus I3. Substituting our calculated values yields 700 milliamperes. P1 equals V1 times I1. Substituting our given values demonstrates that R1 dissipates 4.5 watts of power. P2 equals V2 squared divided by R2. Substituting our given values demonstrates that R2 dissipates 30 watts of power. Finally, P3 equals I3 squared times R3. Substituting our given values demonstrates that R3 dissipates 7.5 watts of power. Total power equals P1 plus P2 plus P3. Substituting our calculated values yields 42 watts. As a means of checking our work, total power is equal to supply voltage times source current, which similarly yields 42 watts. I've got a reasonable degree of confidence our answers are correct, and we can move on to our final illustrated example. Alright, our final illustrated example features a 310 milliampere current source and a parallel combination of R1, a 60 ohm resistor, R2, an unknown resistor, and R3, 200 ohms. We additionally know that current through resistor 1 is 200 milliamperes. We're being asked to solve for the voltage drop across each element, the current through each element, the power dissipated by each element, the source current, and the total power. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Voltage across elements in parallel is the same. The voltage induced by the current source is equal to V1, which is equal to V2, which is equal to V3. Kirchhoff's current law. Source current comes out and splits into three paths. For this circuit, I source equals I1 plus I2 plus I3. Finally, power in equals power out. For this circuit, power total equals P1 plus P2 plus P3. The voltage drop across resistor 1 is equal to current through it times its resistance. Substituting our given values demonstrates V1 to be 12 volts. Voltage across elements in parallel is the same. The voltage induced by the current source is equal to V1, which is equal to V2, which is equal to V3, and they are all equal to 12 volts. I3 is equal to the voltage across it divided by its resistance. Substituting our given values demonstrates I3 to be 60 milliamperes. An algebraic rearrangement of the Kirchhoff's current law equation for this circuit, solving for unknown current I2, demonstrates I2 to be the remaining 50 milliamperes. R2 equals V2 divided by I2. Substituting in our given values demonstrates R2 is 240 ohms. P1 equals V1 times I1. Substituting our given values demonstrates R1 dissipates 2.4 watts of power. P2 equals V2 squared divided by R2. Substituting our given values demonstrates R2 dissipates 600 milliwatts of power. Finally, P3 equals I3 squared times R3. Substituting our given values demonstrates R3 dissipates 720 milliwatts of power. Power total equals P1 plus P2 plus P3. Substituting our calculated values demonstrates that total power is 3.7 watts. As a means of checking our work, we could solve for total resistance. The total resistance of a parallel combination of R1 and R2 and R3 is equal to 38.7 ohms. Power total is equal to source current squared times total resistance. Substituting our given values similarly demonstrates total power to be 3.7 watts. I've got a reasonable degree of confidence these answers are correct, and we can end this lecture. In conclusion, this lecture examines several illustrated examples of parallel DC circuit analysis featuring unknowns. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.